Hello, welcome to the 0th episode of Concatenative Explorations. I'm Alex, and today we will not be talking about concatenative calculus yet. I want to introduce you to the tool that we will be using throughout the series. This is a web-based tool that I made specifically for this. It's called Concatenative Evaluator, and you can find a link to it in the description. If you prefer a textual introduction, you can find a link to the README in the upper right corner, but I will describe everything here in the video. The first time you load this page, you will see some default definitions. We will not be using them today, I'll just delete them. And let's start at the bottom. Concatenative Evaluator is an expression rewriting engine, so you provide it with an expression. And an expression consists of words separated by white space. And words can be anything. Letters, numbers, symbols. This is a word, this is a word, this whole thing is one word. And you can use arbitrary strings of characters to name your words, with a few exceptions. Parentheses are words indicating comments. So you can see this comment does not appear in the evaluation, and they can nest. The other special words are brackets, which are used for quoting arguments to operators. You can put arbitrary expressions inside, and they also nest. When you have an expression, you can step through its execution, 1 step at a time, 5 steps at a time, or you can provide a multiplier and step through multiples of that multiplier. On each step, the engine will seek a pattern and replace it according to a substitution rule. For now, nothing happens because we didn't define any substitution rules yet. The basic way to do that is to add an operator. An operator's definition consists of its arity, how many arguments it takes, its name, which can be any single word, and the substitution pattern, which, as you can see in the example, is just like an expression, but instead of words, it uses numbers that refer to the arguments. We will define this dupe operator to duplicate its argument. So the substitution is just the quoted argument repeated twice. Now, whenever the evaluator finds one argument followed by dupe, it will replace it with twice of this argument. Let's test that. Let's say we have an A and we want to dupe it. We can make a step, and you can see A got captured as the first argument and replaced by a substitution. If instead this was some more involved expression, this whole part would be captured and correctly duplicated. So these arguments can capture the entire quoted expression. Another way to define stuff is by adding a word. Words, unlike operators, don't take any arguments, but their substitution rules can be any expression you want, using any words you want. We can define a toDupe that just does dupe twice. And wherever the engine finds toDupe, it will replace it by its body. Now this is a dupe definition, so it will get substituted. And this is a dupe definition, so it will also be substituted. And we have reduced our expression. Words can freely refer to themselves. Let's say that infDupe is dupe followed by infDupe. Note that infDupe is a single word, and this dash in the middle is just a character, it doesn't have any special purpose. If we try it out, the first thing that it will do is replace infDupe with its body. dup inf_dup. Then this is dup's definition, which will perform its substitution. But after that, we still have an inf_dup. So it will be replaced by its body again. And there is another valid dup substitution, which will happen. And then an inf_dup substitution will happen, and the dup substitution will happen, and so on and so forth. And if we step through 500 steps, you can see these A's are being duplicated into infinity. This is why there is no step until the end button. It's very easy to make expressions that never finish evaluating. The last kind of definitions you can make are using natural numbers. If you just put numbers in an expression, they don't do anything. They're not defined as words, they're not defined operators. There's nothing to substitute. We can then define a zero expression, which can be any arbitrary expression you want. And if we enable it, zero will start acting as a word defined with this as a body. So if you see, if we step now, zero gets substituted with the appropriate body. To get all natural numbers, we can also define a successor expression. And if we enable that, any natural number will be reduced by zero, followed by an appropriate amount of successors. So 0 is still just a 0, but 1 will be definition of 0 and 1 successor. 5 is 0 and 5 successors. And 9 is 0 and 9 successors. The definitions I wrote here don't make much sense, but you can come up with definitions that are actually useful and achieve arbitrary arithmetic with them. This has been the main functionality of the evaluator. In addition to that, on top there are some button to load presets of operators. This is the one you start with, and there are 3 more you can choose from. Alternatively, you can export and import your definitions to and from a text file. It will save all operators, number definitions, word definitions, and the expression, if you have one. Export allows you to save them on your computer, and import allows you to load them from a saved preset. I can load my favorite preset, and you can see I have some definitions of operators, the numbers are defined, there are some arithmetic words, and no expression in this one. And that's the core functionality, as much as we will be using it in the series. But for the sake of documentation, I would like to also talk about the export-import format, because it's actually a human-readable format that you can edit within your text editor. So let's quickly hop to Vim, and you can see an example concatenative calculus evaluator file. Just as the web version, this one has 4 sections: the operators, the arithmetic definitions, word definitions, and the expression. Each section is separated from the others with 2 new lines, which is important because if you want to remove a section, you need to keep it empty and still separated by 2 new lines. So in this case, if we just remove these 2 lines, then there's a new line after this line, new line after this line, and new line after this line. That's just 3 new lines. That's not enough to separate a section that is supposed to include an empty section between. So we need to add 1 more. And now there's a pair of new lines after these 2 lines, an empty integer natural number sections here, and 2 new lines in these 2 lines. Now, each section has its own syntax, but they're very similar to each other. The most complex one is operators, which start with a natural number indicating arity, or how many arguments the operator takes, then the name of the operator, and the rest is an expression, but it doesn't have to be a real expression to be imported properly. Even if you make a malformed expression, it will import, but it will throw an error in the web interface. So you can debug it over there. And each line is its own definition. Now, the natural numbers section that we removed, only 2 lines of it matter. Any more will be ignored. And these are definitions for 0 and successor. They don't need any names or arity. So these are just expressions, 1 in each line. The third section is word definitions, which do include names. So the first word in each line is a name of the word. And then the rest, again, is just an expression that will be verbatim copied and imported. And finally, the expression is just loaded without any processing. Anything that's after the third section, separated by 2 new lines, will be loaded, preserving all formatting, all spaces, and without any parsing. So it can also be a malformed expression, just as all of the others. And that concludes the tour of the concatenative evaluator. If you still aren't sure how it works, you can try reading the README in the upper right corner. And if after that you still have some questions, feel free to find me on the EzoLang's Discord server, which will be also linked in the description. So that's been all for today. Thank you so much for watching, and I'll see you in the first episode of Concatenative Explorations.